So to set up our discussion for the second law of thermodynamics, let's actually start by talking about the first law again. So we know that the first law tells us that the change in the internal energy of a system is equal to the energy you transfer in or out as heat minus the work done by the system. So what does the first law tell us about an isolated system? Well, if your system is isolated, it cannot exchange energy or matter with its surroundings, which basically means you can't add in energy as heat because it can't exchange energy, it can't do work. So therefore, for an isolated system, the energy of an isolated system is constant. Mathematically, this just tells us that the change in the energy of an isolated system is equal to zero. Okay? Well, second law of thermodynamics tells us that the entropy, and we'll come back in a second to what that is, of an isolated system cannot decrease. So notice here, this is not as simple as, so S is the letter we use for entropy. It's not as simple as the change in entropy is equal to zero for an isolated system. It's the change in entropy is greater than or equal to zero for an isolated system. And so that equation becomes equal to zero, so the change in entropy is equal to zero if your process is reversible. It's greater than zero if your process is irreversible. And so one way to think about these two things is that a reversible process is a process that can be reversed so that it leaves no change in either the system or its surroundings. Another way to think about reversible versus irreversible is, in some sense, the way we know time, or how we think about things behaving in time, is tied up in this idea of whether something is reversible or irreversible. So if I were to take, say, a pendulum and let it swing back and forth, and again, let's say I've got a pretty good pendulum so it doesn't lose its energy very quickly, and I don't show you too long of a clip, basically that seems reversible because you can't tell whether I'm running the video backwards or forwards. If, on the other hand, I let that video go for too long, well, you clearly at some point, if you were to watch it for 5 minutes, you would watch it come to a stop. So if I ran that video backwards, you would watch a ball basically a mass hanging on the end of a string straight down, and then for no apparent reason whatsoever, start to swing slightly side to side, and then it would pick up and swing more and more. And it would be clear to you that you were watching the movie backwards as opposed to forwards. So when it's clear which direction you're watching the film, that tells you have a irreversible process. When you can't tell, that's one way to think about a reversible process. So a reversible process is really just an ideal process. And we'll talk about plenty of idealized processes, but when we talk about reversible processes, we really just mean this idealized situation. In the real world, processes are never reversible. So natural processes are always irreversible. So what the second law, or one way to think about what the second law is trying to tell us, because there's actually quite a few sort of variations of it, but one of the way to think about what the second law is trying to tell us is it says when all the systems taking part in a process are included, the total entropy cannot decrease. So if you add up the change in entropy of all the pieces that are exchanging energy back and forth, the total entropy of your system cannot possibly decrease. So as an example, let's start with two isolated containers, each of which hold a kilogram of water. So here, I've got a kilogram of water at 40 degrees Celsius. Here, I've got a kilogram of water at 60 degrees Celsius. And again, we know from our calorimetry problems that when I put this together, they're going to exchange energy, so that if I combine the water in both containers and then wait, that basically, assuming that I don't have any energy, I'm not letting the water in these two containers be exchanged with their surroundings. So I just have the energy that's inside my little box here. And so those 2 kilograms of water are going to rearrange their energy so I end up with 2 kilograms at 50 degrees Celsius. Right? The cooler water will increase 10 degrees, the warmer water will decrease 10 degrees. So the idea is that the energy within the system, so my 2 kilograms of water in my system, the energy within that system has been rearranged, right? Some energy was transferred as heat from the hotter water to the colder water. But we still have the same total energy as what we started with. So I haven't changed the energy in my system. Again, delta E is still 0 here. But what I have done is I have increased the entropy. And so basically the reason that I end up with all this water at 50 degrees Celsius is because that gives me the maximum possible entropy change. So I've actually increased the entropy to as large a value as it possibly can be. In some sense, what I've done is I had water at 2 different temperatures, which means that I had the ability to basically set up an engine between these two, use them as thermal reservoirs and set up an engine between these two and let the heat transfer produce some mechanical work. But now that all that water's at the same temperature, I don't have that ability anymore. So what I've lost here is the opportunity to convert some of that energy into work. So in increasing the entropy, basically I have lost the opportunity to get some of that energy to be positively transferred into work. That's one way to think about what's going on with this concept of entropy. That it's giving us a measure. Low entropy means that you've got a fairly large amount of useful energy. High entropy means that you've lost that opportunity to use the energy. So if I've got a reversible isothermal process that goes from state 1 to state 2, we define the entropy change to be, so delta S, the entropy at state 2 minus the entropy at state 1, right? This is just final minus initial. It's the heat added or removed from the system as heat divided by the absolute temperature of the thermal process of the isothermal process. So again, our isothermal process occurs at a single temperature, so this is that temperature. The absolute temperature tells me that I want it in Kelvin, so I want the temperature in Kelvin, and then I want to know the heat that was transferred in or out. That's going to let me calculate the change in entropy of my system. So obviously, since the units of energy transferred as heat are joules, and I want absolute temperature that's in Kelvin, this tells me that the units of entropy are joules per Kelvin. And I also notice that I can have a positive or negative change in the entropy by basically making this term, right, my energy transferred as heat, either positive or negative. So my absolute temperature is always going to be a positive number, right? Kelvin, right? We can't get to 0 Kelvin, so we're always going to be at some positive temperature. So whether my change in entropy is positive or negative is really just an issue of whether or not this energy transferred as heat is positive or negative. So when energy is transferred into my system, whenever my system adds energy as heat, then the entropy change has got to be positive. When my system gets rid of energy as heat, then my entropy change has to be negative. So having a positive or negative change in entropy for a particular piece involved in your process is really just an issue of thinking about whether or not that particular piece adds or gets rid of energy as heat. So let's come back to think about our example here. And so we know that with my cool water that started at 40 degrees Celsius, it was clearly going to take in energy as heat. So Q for the cool water, for my cold water, that's got to be a positive quantity, which means that the entropy change for the cold water has to be a positive quantity. For the hot water, well, it's giving up energy as heat, right? That's what the energy that is given up by the hot water is what goes to change the temperature of the cold water. So the Q for my hot water, that's negative, right? It gives up energy as heat, which means that the change in entropy for my hot water also has to be negative. So the question becomes, well, if I can have positive entropy changes and negative entropy changes, then am I ever going to end up violating the second law of thermodynamics, which told me that when I included all the pieces in my system over which energy is being exchanged, I have to end up with a non-negative number, right? It can't decrease. And so for this particular process, again, we really define this in terms of an isothermal process. But when our temperature does change, all we can do is just break it up into infinitesimally small isothermal steps and then use calculus to get what our answer will be. So I can do that sort of qualitatively in thinking about this problem. And so when I want to think about, does this violate the second law? Well, again, the second law tells us that we've got to include all of the systems taking part in the process. And so that means I got to take into account both the change in entropy of the cold water and the change in entropy of the hot water. Well, I know that the change in entropy of the cold water is going to be positive. The change in entropy of the hot water is going to be negative. And so really this becomes an issue of how much does the entropy change for the cold water compared to the entropy change of the hot. Well, I can calculate, so think about some tiny little chunk. If you want to think about, say, sort of the first degree. So as the hot water went from, it gave up enough energy to go from 60 degrees Celsius to 59.9 degrees Celsius, and the cool water took in enough energy to go from 40 degrees Celsius to 40.1 degrees Celsius. So again, that energy transfer, I know that the energy taken in by the cool water is just going to be negative the energy given up by the hot water. I know, but I also know that the temperature at which the cool water, that process is taking place, is basically 20 degrees less than the temperature at which the temperature at which the hot water is giving up that energy. So when I look at these two equations, QC and QH both have the same value, opposite signs, but TC is a smaller number, right? That colder temperature is going to be a smaller absolute temperature than the hot temperature. So when I divide by a smaller number, that tells me that the magnitude of the entropy change for the cold water is going to be larger than the magnitude of the entropy change for the hot water. So when I add them together then, that means that the total entropy change for my system is going to be a larger positive number plus a smaller negative number, and sure enough, that gives me a positive change in entropy. So what the second law is telling us, the second law of thermodynamics is trying to make very clear, is it's okay for pieces within your system to have an entropy decrease. But that has to be compensated for by an entropy increase that's even larger, or is at least as large, if not larger, by the other parts of your system in terms of where this energy is being exchanged around. So that's why we always end up with a entropy change that never decreases. And so sure enough, our process here doesn't violate the second law of thermodynamics. It's actually following the second law of thermodynamics, and it gives us the largest increase in entropy, which is basically the way nature seems to behave, is it will take the largest increase in entropy it possibly can for any particular situation.